Okay, so Happy New Year, everyone. Thanks a lot for joining this YRQG seminar. This will be the last seminar in our mini-series on quantum cosmology. And today our speaker is Yili Wang. She graduated in 2016 from Shanghai University and then went on to do her master's studies from 2016 to 2017 at Imperial College London. Afterwards, she became a doctoral student in Daniele Oriti's group in Munich, and she finished her PhD there last summer. Since then, she's a postdoc at Hanyang University, and her research focuses on considerations in the framework of alternatives to Einsteinian gravity as well as quantum gravity. And today, Healy will talk about the effective anisotropic dynamics in group field theory cosmology, which is also the subject of her latest publication. So thank you very much for accepting our invitation and for being here today. And feel free to start whenever you're ready.
Okay, then I'll start right now. And thank you for invitation. And I really appreciate this opportunity to share my recent work with Daniele Oriti on the GFT group field theory cosmology. So my talk consists of 4 parts. And now let me first start with the background of our research. We know that at large scale, our universe can be well described by the standard cosmological model, which states that the universe is homogeneous and isotropic. However, this model contains an initial singularity which hasn't been resolved yet. Therefore, some people may think of the quantum gravity effect on the cosmology and to see whether such initial singularity can be resolved. For example, in loop quantum cosmology, such a singularity can be replaced by a big bounce. And also we expect that some other approaches to quantum gravity can also give us some resolution of this singularity as well. And then here comes the second challenge, is that when we are approaching the singularity, the universe is at very small scale. So it's not necessarily to be isotropic anymore. Instead, there is a so-called BKL conjecture. This conjecture tells us that the anisotropic approach to the singularity is more generic than the isotropic ones. And the evolution of this small-scale early universe near the singularity can be described by a classification of anisotropic model named Bianchi model. So our work I'd like to show you today is to give it a try to see whether we can construct a state in quantum cosmology which describes the early evolution and explain the late acceleration of our universe. And our strategy is quite straightforward. So first of all, we will choose a classical model, and based on this model, we try constructing its quantum cosmological correspondence. Then, by comparing the observables and effective dynamics over this quantum state with its classical counterpart, we can see whether our construction can effectively reproduce the continuum classical universe. The quantum gravity model we are interested in here is named group field theory, GFT. This is also a non-perturbative approach to quantum gravity. This means that we have no background spacetime or coordinate system because of the diffeomorphism invariance, and so the background manifold of the coordinate are not physical. Instead, we will use the relational description. So in this way, the reference frame is also dynamic object. And here, the matter's degrees of freedom can help us relationally describe the evolution of our state. And before we go further with GFT, let's first go a review on the classical universe that we are interested in. So at classical side, we will study the Bianchi-like universe. This is the simplest, spatially homogeneous and anisotropic model from the Bianchi classification. We choose this model because it's simple, and so far, the GFT cosmology is still at the very beginning stage in describing the anisotropic universe. So this Bianchi-like universe can be characterized by 3 different scale factors, this A1, A2, A3 shown here. We can see that since it's homogeneous, so there is no need for us to introduce any spatial dependence on it, and everything only depends on the temporal direction tau here. For our future convenience, we can rewrite these scale factors in terms of the Misner's variables, this beta plus, beta minus on the right-hand side. And then, of course, they will also only depend on the temporal direction as well. Now, as I mentioned before, that we will make a comparison between the classical universe and the quantum cosmological model, which is described by a relational reference frame. Therefore, in order to make this comparison more straightforward, we will also couple this classical universe with a meta reference frame. And here we use the minimally coupled massless scalar field. Because it's homogeneous, so we only need one scalar field and make it acting as a material clock. The value of this clock can tell us how to describe the evolution of the universe relationally. And then we can write down the equations of motion in terms of the value of the scalar field. We can see that on the right-hand side, there is an extra contribution from the anisotropy. If we remove this term away, then of course we will go back to the Friedmann's equation. And this equation can also be solved. We can find that the right-hand side is actually a constant, no matter we are in the anisotropic case or isotropic case. Therefore, by only studying the behavior of the volume on the left-hand side isn't enough to tell us whether we are in an isotropic or an anisotropic universe. Therefore, we need further measures of anisotropy to tell us the property of the space-time we are working with. A very common choice on measure of anisotropy in cosmology is the anisotropy parameter A here. It is defined by the Hubble parameter on each direction, hi, and the mean Hubble parameter h. We can easily check that this quantity goes to 0 if we are in an isotropic FLRW spacetime. Now, we want to know if there are any more measures of anisotropy that we can have. So we may think that maybe Misner's variables can also be some good quantity for us, because we know that when we are in an isotropic universe, the Misner's variables, those beta, becomes 0. However, before we choose this to be a measure of anisotropy, let me make more comments on it. So here, a very important thing that we need to keep in mind is that the Misner's variables are not unique quantities to characterize a Bianchi-like spacetime. So here is a very simple example which can illustrate it. So now suppose we have the first observer, and this observer uses this beta plus and beta minus to characterize the Bianchi universe. Then we have the second observer, and this observer has another set of Misner's variables, the beta tilde on the right-hand side. And these 2 sets of Misner's variables are related, for example, in this way. Of course, there will be numerically definitely different things. However, we can see on the right-hand side that actually these two different sets of Misner's variables give us the same universe. The only difference comes from the choice on a preferred set of coordinate system. So if we want to use the Misner's variables as a measure of anisotropy, we should always keep in mind that once we made a specific choice on it, the following computation and investigation must be inconsistent with a choice that we made at the very beginning. And now, having reviewed the Bianchi-like universe, let me give a very short introduction to the group field theory approach to quantum gravity. So the group field theory, GFT, as its name implies, describes the field theory on a group manifold instead of a background spacetime. And the basic dynamic object, such a field labeled by this phi, is having some variables which are group elements. Here we choose the group to be SU2 group, so we can borrow techniques from loop quantum gravity or loop quantum cosmology. And such a field represents the basic building block of our space. Now we are dealing with a three-dimensional space. So the GFT quanta are the tetrahedron, which contains 4 faces. And such a tetrahedron can also be represented by a 4-valent spin network. Each link of the spin network corresponds to the face or the triangle of such a building block, and the vertex of the spin network corresponds to the tetrahedron itself. And in order to describe the evolution of such thing, we will use, as mentioned above, the relational reference frame. And here we again coupled it with a massless scalar field. The value of the scalar field will be assigned on the vertex of the spin network. And we can see that the dynamics of such a tetrahedron is governed by such an action. And I'll show you the kinetic kernel later, but here I'd like to mention that in our work, we assume that the interactions among the tetrahedron is almost negligible compared with other terms. Now, we have known that the basic building block of the space and the dynamics it should satisfy. How can we reconstruct a classical continuum universe from this quantity? In order to do so, let me introduce the strategy named GFT quantum gravity condensates. So we will begin with the GFT quanta I introduced right now, and then we will define a GFT condensate state. This condensate state will contain a large number of the tetrahedra or the GFT quanta, and then we will only study the collective behavior of this large amount of the quanta effectively, and then we can find its observables and also the effective dynamics over such a state and compare it with the classical dynamics. The previous study in GFT cosmology has shown that the GFT condensates can successfully reproduce the Friedmann equation effectively. Therefore, we also want to know that whether such a strategy can help us construct an anisotropic universe. So here is the explicit definition of the GFT condensate state. We can see that this cat sigma is defined in a very similar way with the coherent bosonic state in condensed matter physics. So here we have a superposition of many tetrahedron. However, each tetrahedron are characterized by the same wave function, the sigma here, and this emphasizes the homogeneity that we want. So this condensate state it satisfies the dynamics we called the Schwinger-Dyson equation, which can be derived from the action that I mentioned previously. And now, here, this is the explicit form of the kinetic kernel that we want to use. By this choice, we will have a GFT model based on the EPRL spinform model. And also, such a kinetic kernel can make GFT a renormalizable theory. So, we want to study the effective dynamics of it. Therefore, we need to know the behavior of such a condensate state at some specific time point, or the specific value of the scalar field. And now maybe let's go back. For example, we want to know how this condensate state behaves at some scalar time phi 0. A very straightforward way may be to insert a delta function in this wave function sigma. Then this will pick out a time point and tell us the behavior. However, simply inserting a delta function will bring us a diverging quantum fluctuation, and this is not what we want. Therefore, we will instead apply the coherent peak state. And we can see the explicit definition of it shown here. It has a shape which also has a peak, but now the typical width of this peak is small but still finite. And in this way, we can control the quantum fluctuation and it becomes non-divergent. So the calculation will be more reliable after we applied such a coherent peak state, and the peak of this function will be used as the relational time, this phi 0 here. The observables of interest in our work are the number operator, the volume operator, and the area operator. So the number operator is defined in a very usual way. This number operator will count the number of the GFT quanta or the tetrahedron in our condensate state. And the second, the volume operator, it has some eigenvalue, depends on the intertwiner assigned on the vertex of the spin network. And this VJ1234 denotes this eigenvalue. And finally, is the area operator. This eigenvalue depends on the spin assigned on the links of the spin network. And we know that such link corresponds to the triangle or the face of this tetrahedron. So this will give us the area of this triangle. And now let's see how to define an anisotropic GFT cosmology in the language of GFT condensate state. Before we define anisotropy, we should first figure out what do we mean by isotropy in GFT. The point is, in GFT, the isotropic tetrahedral geometry is specified by only one single variable, and this variable specifies the tetrahedron's volume. However, this can be realized by various kinds of configurations. And usually we have two different ways to define isotropy in GFT. So in first case, we use the regular tetrahedron as the building block of an isotropic space. And in this case, the four faces of one tetrahedron are exactly the same, and the volume of such a tetrahedron is maximized in order to control the shape and make it regular. And this definition is most commonly used in GFT cosmology. And the second definition, if you're familiar with, then you will see that it's quite close to the definition in loop quantum cosmology. So here we use the tri-rectangular tetrahedron as the building block of our space. And this tetrahedron has three edges meeting at some point, for example, D here. So if AD, CD, BD shares the same length, then we say that this is a building block for an isotropic space. So we can parallelly develop two different kinds of anisotropic state in GFT cosmology based on these two different definitions. And we can also make comparison between these two models to see whether they will yield the same qualitative behavior. And before doing that, there is still one problem that we need to be solved first, is that we have no quantum operator which measuring anisotropy. As we can see in the previous section that at classical side, we have some measures of anisotropy, and this will tell us the property of the universe. However, there is no corresponding quantity in GFT, which means that we can't do a direct comparison between two sides. However, we can play a trick here. So, which means that we first study the relationship between the measure of anisotropy and some geometric observables, such as the volume or the area. And then we can substitute the eigenvalues of these operators into this classical expression and assume that they approximately satisfy the same relation for the quantum state we have. And so these quantities will be treated like some anisotropy eigenvalues. And I'll show you more explicitly now. So let's start from the first definition, where we use the regular tetrahedron as the building block of an isotropic space. In order to find the relation between the measure of anisotropy and the geometric observables here, we first suppose that we have some regular tetrahedron first, and then we embed it into an Bianchi-1 space. So now the background is anisotropic. So the shape of this regular tetrahedron will be changed. And we can find how the Misner's variables, the ratios between the scale factors and the anisotropy parameters related with areas or the volume of this, the changed shape of this tetrahedron. Of course, you may find out easily that the relation I show here is closely related to how we embed such a tetrahedron. For example, a different way of embedding will result in different relations. However, this is not a problem. So we already know that the Misner's variables are not unique to characterize the Bianchi-1 universe. And here, similarly, the different ways of embedding is simply show some different preference on the spatial directions that we want to use. And so we still need to keep in mind that once we specify the way of embedding, then everything done in the following should be inconsistent with this choice as well. And now we have known that how in classical side we can write the measure of anisotropy in terms of geometric observables. Then we can change the shape of the tetrahedron according to this embedding first to define the anisotropic condensate state. So here on the right of this slide, I'll show the spin networks that we contain in our GFT condensates. This contains all possible spin networks that we can have. So here, we called the isotropic part as background and the anisotropic part as perturbation. But this doesn't mean that the anisotropic part isn't important or subdominant. Actually, this is simply because that we want to recover the Friedmann equation, the isotropic dynamics, at a later stage. So at this stage, the isotropic part must be dominant, and that's why we call it some background, and the anisotropic part, the perturbation. And then we can also solve the equations of motion and find the wave function assigned on the GFT condensates according to this choice here. So here, this is just the solution of it. And the first thing that we can study, which is the most straightforward one, is the number operator and its expectation values. So this can be directly get from the GFT wave function. And so now we don't care about the explicit numeric value of it. And actually, we only care about the ratio between the isotropic part over the total number that we have. So here we can see that the behavior of this ratio is symmetric around some clock time point. Here we choose it to be 0. And this is something very similar with a bounce. And then we can also find that such a ratio goes to 1 at a later stage. So this means that the isotropic part of the isotropic tetrahedron will governing our condensate state at a later stage, though this state is anisotropic at early time. And it's also very interesting to find that actually it's not simply that the isotropic part is dominating, but actually it's the isotropic part with the smallest spin is dominating at a later stage. And this agrees with the previous study in GFT cosmology, which find that at a later time, the GFT condensate will be dominated by the spin networks with the smallest possible spin. And then let me show how can we define the GFT measure of anisotropy. So first of all, we have some classical relation between the measure of anisotropy. Here is the Misner's variable and the area of the tetrahedron, the area of the triangles. And here we simply substitute the area eigenvalues into this relation, and we will get some corresponding GFT definition of Misner's variable. And then we will do an average over it to make it an intensive quantity. And then this is the final quantity that we want to study. So similarly, there is still something like a bounce at some clock time. And also, though the state is anisotropic at early time, the variables become 0 later, and so our state becomes isotropic. And the similar thing can be done for the ratio between scale factors, and so the conclusion is also the same, and we can also study the anisotropy parameter and find just exactly the same result. And now let's check another definition and to see whether it will give us the same conclusion. So the second definition uses the tri-rectangular tetrahedron as the spatial building block. Here again, we just embed it into a Bianchi-Wang universe. And of course, the shape of this tetrahedron will be changed again. And we can find another set of relations between, for example, the Misner's variables and the areas of this tetrahedron. And so, of course, we can play the same trick and just substitute the eigenvalues into it and define the GFT observables according to this one. So we find that here we still include some isotropic background and some anisotropic part. And we find that though the definitions are different, the qualitative behavior is exactly the same. So now, just according to the observables, we can find out that the state is somehow anisotropic at early time, and it gradually becomes isotropic later. And now I'd like to show the reliability of the calculation here. So in order to do so, we just compute the relative variance of these observables that we calculated previously. And it is easy to find that the volume operator and also the geometric operator, like the area operator and also the number operator, they all have very small relative variance when the number of the tetrahedron is very, very large. However, we also compute the anisotropy. And however, we know that we have no corresponding operators. So actually, the quantum fluctuations of these quantities is still an open issue. However, here I'll just show you a very simple analysis, and to prove that at least our calculation here still has a controllable quantum fluctuation. So we can just go through like how we defined the quantity in GFT. We start from the classical side and defined the corresponding GFT quantity. And then we do a sum over these quantities. And we can see that this definition is exactly the same with the volume operator, for example. And so this beta plus and beta minus in GFT is also treated like something like VJV on the left-hand side. This means that we treat them as some eigenvalues. And so basically, the relative variance should be qualitatively the same with the geometric operators such as volume and the area operator. Therefore, therefore, at least in such way of definition, the relative variance is also negligible if the number of the tetrahedron is large enough. And now, finally, we want to check whether we can reproduce an effective dynamics from our GFT condensate, which can capture the same features with the classical dynamics. And so here, the first line, I show the classical dynamics of the Bianchi-like universe in terms of the scalar field. So we expect that the GFT can also yield some similar equations of motion. And however, as we know that the right-hand side is a constant, no matter we are in isotropic or anisotropic universe. Therefore, all these three quantities should be studied and to see which part contribute most. Of course, it's not surprising that when at a later stage, when our state is governed by isotropic building blocks, we will get some effective Friedmann equation describing the isotropic universe. However, we also find that, for example, here, between 5 to 10, when the isotropic GFT quanta are not dominant yet, our dynamics shown below still satisfies some Friedmann dynamics. So it may imply some incompleteness in our construction and give us some guidance for future construction. So here, let me conclude. In our work, we start from the GFT quanta and defined the anisotropic GFT condensate state. Then we studied observables and its effective dynamics to see whether it can describe the early stage of our universe and yield some isotropic dynamics at a later time. By comparing it with the classical universe. And so here we made the following improvement compared with the attempt which has been done previously in GFT cosmology. So first of all, we used the coherent peak state, which means that now this time the quantum fluctuations from our state is controllable and non-divergent anymore. And second is that we also find that our state can be dominated by the smallest spin networks at a later time. And third, I think it's also a very important improvement is that we use all possible measures of anisotropy and to check whether all these themes can give us a consistent result. And finally is that we include as all possible spin networks in our condensate state to make our state as general as possible. However, there are still many open issues. So as we know that we have no operator measuring the anisotropy yet. So in order to make the construction more reliable and make the comparison more straightforward, it will be interesting and important for us to find if there is such an operator that can tell us how anisotropic is a state. And also, like at the beginning, I mentioned that we neglect the interaction between the tetrahedron. However, the interaction among the tetrahedron may become important when we approach the singularity, and we also expect that the inclusion of the interaction may yield some interesting prediction for the early universe in language of GFT cosmology. That's all. Thanks for listening.
Okay, yeah. Thank you very much for this nice talk. And let me stop the recording.